sklearnnaivebayesCategoricalNB. Description: Categorical NB is a naive Bayes classifier designed specifically for categorical features. It operates based on the principle of Bayes' theorem, assuming that features are conditionally independent given the class label. Inputs: X, a 2D array of shape n samples. N features representing the training data, where each row corresponds to a sample and each column represents a categorical feature. Y, a 1D array of shape n samples, representing the target class labels for the training data. Outputs: self, the fitted categorical NB estimator. Predict prob X returns the probability of each class for the input data X, represented as a 2D array of shape n samples. N classes. Predict X returns the predicted class labels for the input data X, represented as a 1D array of shape n samples. Steps. Training phase. Calculate the prior probabilities of each class based on the training data. Calculate the conditional probability of each feature value given each class, using the frequency of each feature value within each class. Prediction phase. For each new sample, calculate the posterior probability of each class using Bayes' theorem, taking into account the prior probabilities and the conditional probabilities of the features in the sample. Assign the class label with the highest posterior probability to the sample. Metrics. Accuracy represents the proportion of correctly classified samples. Precision measures the proportion of correctly predicted positive samples among all predicted positive samples. Recall measures the proportion of correctly predicted positive samples among all actual positive samples. F1 score the harmonic mean of precision and recall. Visualization plots. Confusion matrix visualizes the distribution of predicted and actual class labels, revealing the types of errors made by the model. ROC curve plots the true positive rate against the false positive rate for different classification thresholds, providing insights into the model's performance in distinguishing between classes. Fine-tune parameters. Alpha, a smoothing parameter that helps prevent overfitting by adding a small value to the counts of each feature value. A larger alpha value implies stronger smoothing. Uncertainty methods. Confidence scores. Categorical NB can provide confidence scores for its predictions, indicating the probability of the predicted class being correct. Challenges and fixes. Challenge 1. Data sparsity. If the training data contains infrequent feature values, the model might overfit and make inaccurate predictions on unseen data. Sample use case. A dataset with a large number of categories for each feature, but only a few examples for each combination of categories. Fixes. Increase the size of the training data to improve the statistical significance of the feature. Value counts. Apply feature engineering techniques like combining infrequent categories or using a smoothing parameter alpha to reduce the impact of sparse data. Challenge 2. Feature independence assumption. The assumption of feature independence may not hold in real-world datasets, leading to biased predictions. Sample use case. A dataset where features are correlated. For example, features describing different aspects of the same entity. Fixes. Explore using more sophisticated algorithms like Bayesian networks or decision trees that can handle feature dependencies. Perform feature selection to remove redundant or correlated features before training a categorical NB model.